Well, hello everyone. Welcome to our next lecture of this topic, that is context-free language and context-free grammar. So, let's start with what we are going to study today. So, in today's lecture, we are going to first of all take the overview of our last lecture, whatever we have done so far in this particular topic. Then we will move on to identification of context-free grammar. We had picked already that what is grammar. So, in today's lecture, we are going to specifically identify that what is context-free grammar. Further, we will move ahead with leftmost derivation and rightmost derivation. In previous lectures, we have started with Chomsky hierarchy, where we had picked different types of grammars. We had picked regular grammar, context-free grammar, all those stuff. Then we moved that for any specific language, we require grammar. So we had identified that what is actually grammar. We had picked that grammar is having four tuples: variable, terminal, production, and starting symbol, VTPS. We had also picked a few examples of grammar, how to identify all the tuples from that grammar, and how to derive any specific word or a string if any specific grammar is given. So all those stuff we have done in our previous lectures. Now today let's start with our context-free grammar first of all, and then we will move further. Now what is actually context-free grammar? Context-free grammar consists four tuples: variable, terminal, production, and starting symbol. Now, what is V? We have already done with respect to our definition of grammar. So, V is set of variables, which is again it can be called as non-terminal. T is set of terminals, which is called sometimes non-variable. Then P is production rules, which is written in terms of variable is producing lots of rules, alpha 1 or alpha 2 or and so on. Here alpha I is an arbitrary string of variable and terminal, as we have already done all those stuff in our grammar. So definition of context-free grammar becomes quite easy to understand and interpret. Now S again is a start symbol. Now let's take one example of context-free grammar, uh, that is binary palindrome. Means if I have combination of 0 1, and if I'll write 0 1 0 or 0 1 1 0, means if I'll start with left to right or right to left, it will be equal from midpoint. That is palindrome. I hope you already know the meaning of palindrome. For example, uh, let's take one word, that is madam, M-A-D-A-M. That is palindrome. It starts with M-A, and once, or if I'll read from left to right or right to left, I'll get the same meaning. So that is palindrome. Now this particular language is context-free language. Now, first question arises that why this language is context-free? Why it is not regular? Can you guess the answer of it? The answer of it is in palindrome, from midpoint we need to identify that whatever written in your left side and right side, everything is similar once it is read from both ends. Hence, there is a pure comparative analysis, and we have already proved that in regular, since we do not have any additional memory in finite state machine, we cannot uh, generate any language which is having such kind of comparison. Hence, this language is not a regular language. Now, I can say that I had proof that this is not regular, that from which point I had proved that this is context free. That we will discuss further, that why it is context free. Right now I had given grammar of this particular language, which says for binary palindrome A produces 0 A 0 1 A 1 slash 0/1/epsilon. That is language, and that is grammar of this binary palindrome language. Now let's take example that how actually palindrome works. So as we have earlier discussed that this is the grammar. A produces 0 A 0 1 A 1 0 1 epsilon. Now let's take one example, which is 0 1 1 0, mid I have 1. So if I'll read from this way or this way, this is equal, hence it is palindrome. Now if it is palindrome, now can we generate this particular string from that given grammar? Can we derive it? So let's see how to derive it. As we have earlier done the rule says that pick and choose a sequence of production that would allow us to generate the string. At every step, substitute one variable with one of its production. Now, from where I need to start? I need to start from the starting variable. Right now, we have only one variable, capital A. So I'm going to start. But what I want first, as we have earlier done for derivation, it is left to right movement. So I require 0. So 0, I have two options, either this or this. So since I require more alphabets further also, so I'm going to proceed with this particular thing, that is 0 is 0. So if A is producing 0 is 0, so I got this 0 and this 0. Now I require triple A. So for triple A, I can choose this one, which says now A can be replaced by 1A1, and further A will be replaced by this particular one. Hence I got 0 1 1 1 0. Now as you can see that we have already proved that I can generate one palindrome easily from that from that given grammar. Now the thing is, as we had discussed in previous slides, it's fine that I can say that this particular language, which is for binary palindrome, is not regular, but we have not proved it that why it is context free. What are the characteristics of context free grammar? How to identify if any grammar is given what will be the key highlights through which I can identify that okay, this grammar represent context-free grammar. Now, why I am saying this? Because once we had discussed the definition of context-free, it is same with respect to the definition of grammar which we have done in our previous lectures. That is, any grammar context four things: four tuples, variable, terminal, production, starting symbol. Similarly, in definition of context-free grammar, again we have done the same thing, that context-free grammar consists of four things: variable, terminal, production, and starting symbol. So, how to identify that any particular grammar which is given is context-free or not? For that, there is one major thing through which I can identify, and that I have highlighted here, that says that left hand side of each rule is a single variable. Now, whatever number of rules you are having in your grammar, in each and every rule, that rule should be produced by only single variable. Now, on the basis of this particular thing, I can identify that any particular grammar is context-free grammar or not. Now, let's try to identify from a given rule that which particular grammar is context-free. Now here we are having three examples in front of us. The first one says that S produces A as B, B produces as B, B produces small b, S produces small a. Similarly, there is option B and option C. Now, can you identify that what are different options are representing the context free? So the answer is A and C. Now why A and C are representing context free? As the definition says, context free grammar consists four tuples. Yes, each and every A, B, C all are having four tuples: variable, terminal, production, starting symbol. But the thing is, it differs that in context free, each and every rule will be produced by only single variable. Here in A and C you can identify that each and every rule is produced by single variable. In B, rule number 3 and rule number 4 follow the condition, but rule number 1 and rule number 2 violate the rule, which is single variable will produce the rule. Here, combination of capital A and capital S, these two are variables, are producing certain rule. Hence, in context free, you cannot have these kind of things. Now the thing is, there is one more interesting concept here. Why context free grammar is called context free actually? It's fine, we have picked that for identification of context free we can say that if variable, single variable is producing rule, then, and if all rule are produced by single variable, then we can say it is context free. But the thing is, why it is actually called context free? What is significance of free here? Why it is context free? So the answer lies in the same manner, that if single variable is producing certain rules, it means that particular variable is free from left context and right context. That's why it is known as context-free grammar. Now here, as we can see in particular rules in this B example, if I take A as a prime variable, this A variable is right sensitive to S variable. Hence, it is not free from its right. That's why it is not context free. Hence, you can say this particular example is for CSG, that is superset, as we have done in Chomsky hierarchy, regular language, context-free language, and the next one was context-sensitive. So it is representing context-sensitive kind of thing. Now I hope it's quite clear that how to identify context-free language and why context-free grammar is called actually context-free. So we have done all those stuff today. Now we have identified that what is context-free grammar, uh, why it is called context-free. So let's move to our original aspect, that is derivation. In previous lectures also we have done derivation of a string from any given grammar. Even in today's lecture itself we have done binary palindrome. We have derived one string from that particular grammar. Now let's move into detail of it. That derivation also have two different styles. One is known as leftmost derivation and another one is known as rightmost derivation. Now, what is leftmost derivation and what is rightmost derivation? So let's take one example. There is one grammar. E produces E plus E slash E star E slash bracket E bracket close slash ID. Now, please make sure here this this particular thing is for OR condition, as we had discussed earlier also, that E is producing E plus E, E is producing E star E, E is producing bracket E bracket close, and E is producing ID. Now let's try to derive one string ID plus ID star ID. So if I want to derive this string, in previous class, what we had done, we had randomly picked depending upon our analysis, and we have chosen our variable, that which variable I should proceed first, and we had ultimately derived our string. But in terms of computer algorithms, definitely we require certain way or mechanism. We cannot move in a random manner. Hence, we have two different ways to move to generate particular string. That is, either I can use leftmost derivation or I can use rightmost derivation. Now, let's see further. What we are going to do in leftmost derivation, we are going to utilize this fundamental concept which says always substitute leftmost variable first. If you are having multiple variables, then pick the leftmost variable and substitute it. This is the thumb rule. Now suppose I got E. Now since I want to derive this string, now please make sure this string is having bracket also. Most of the time we forget this bracket. We assume that this is normally written, but it's not a normal thing with respect to string. The reason is we have one particular rule with respect to bracket here. So to get this bracket, we had started that E is producing bracket E bracket. Now for leftmost derivation, it says always substitute the leftmost variable. Now here we have only one variable. Since we have only one variable, we can straight away replace this variable with the suitable next rule, which says I want id plus id, so I have replaced it by e plus e. Now I have two variables and three terminals here. So which variable is the leftmost? That is this particular e. Hence I am going to replace this e, which is from id. Now I got bracket id plus e bracket. Now again I have only one variable left, hence I do not have any choice of leftmost. Hence I am going to substitute this one by e star e. Now again I have two choices, e and e. So which choice I am going to pick with respect to my leftmost derivation? That is this particular e, and I am going to replace this, and this becomes id plus id star e. Now again I have only one e, so there is no choice at all. So I got id plus id star id. Hence I got my desired string by substituting leftmost variable first. So this becomes LMD, leftmost derivation. Now once we talk about rightmost derivation, it again says that yes, I require the same string, but the variable which I am going to substitute first, that is the rightmost variable. Now please make sure reading will be always from left to right. The substitution will be the rightmost variable, so be careful about it. So let's pick again. E is producing this. Now here we got e plus e. Here we had this e. Now here we had this particular e. Here leftmost, and here we are having rightmost. Now I got e plus e, so e got replaced by e star e. Now I have three e's. Now and rightmost one was this one, so this got replaced with id. Further we got two e's, then this got replaced, and finally this e got replaced. So we got the same string, both are equal. The way of representation is different. This is the rightmost variable which is getting replaced, and here we are having leftmost variable which is getting replaced. So that is leftmost derivation style and rightmost derivation style. Let's take another example. Here I have extended that example by deploying this f. We have lots of values of f, and here I am going to utilize the string that is a star ab plus 1 0. Now can you derive leftmost derivation and rightmost derivation of it? Try to derive this thing. So what will be the leftmost derivation? Once again, let's start e star e. Now why? Because I want star here. After that star, what I need to do? I need to convert this into a. So how I'll get a? For A, I need to produce with E is producing F, and then F will give me AF, and further this F will get epsilon. So let's move this. E is producing F, F is producing AF. Now F got null value. So I got A star. Now I have only one variable that is left, that is E. So leftmost, we got the single one, E, and this E should be in bracket terms. So how I'll get a bracket? By this rule, which says E is producing bracket E bracket close. So I have utilized this rule. Now again I have only single variable, but further what I want AB plus 1 0. So I require plus sign, so I am going to utilize the rule E produces E plus E. Now since I have two variable now the leftmost variable is this particular E. So let's start. I am going to replace this E by F. Now what I want AB, and how I can achieve AB? I can achieve by replacing this F first of all by AF, A star AF. Now F and E, the leftmost one is F. Similarly, let's try to derive this thing. Now you can see that each and every time I had picked the leftmost variable. Now be careful, once you want to choose leftmost or rightmost variable, you can identify the leftmost irrespective of any terminal. Be careful, only focus on which one is the leftmost one. Now similarly, here it is the rightmost. You can see whenever we are having two or more variables, what we had done, we had picked the rightmost variable first and try to convert it into terminal format. Once it got converted into terminal, so from the remaining one we had identified the rightmost one and proceed to generate or derive particular string. At the end we got the same string. So that was the leftmost and the rightmost derivation. So there are few questions. Let's check what will be the answer of it. The first question is, for every leftmost derivation there is a rightmost derivation and vice versa. Is this thing is true or false? What will be your answer of it? So the answer is yes, it is true. Once we will move into our next topic, that is parts 3, we will prove it, that every leftmost derivation tree there is a rightmost derivation. Now let's move to the next question. The question is, does every word generated by a context-free grammar have a leftmost and rightmost derivation? According to you, what is the answer of it? So the answer is yes. Once again read the question carefully. Does every word generated by a CFG, if I am trying to derive any string, do I have leftmost and rightmost derivation? We had already done in our previous example that for any given string, I can deploy leftmost or rightmost derivation to generate that thing. These two are way of generating any string, Hence, definitely both can be utilized at any point of time. Now, the last one. Could there be words which have more than one leftmost or rightmost derivation? Now, this is the quite tricky one. Is it possible that for one specific string you can have two or more ways of generating it? Is it possible? So, the answer is yes. But be sure not for all grammars. It totally depends upon grammar. Yes, there are certain grammars in which for any given string we can generate two or more than two leftmost or rightmost derivation tree. Once we will move further, I'll tell you that what are those grammars and I'll provide example of those grammars also. So that's what we have done in this lecture. In next lecture, as I have told earlier, we will focus on derivation tree, which is also known as parse tree. Then we will pick that how to design leftmost derivation tree and rightmost derivation tree. What is LMD tree and RMD tree? In previous slide itself, I had showcased with respect to question that for proving LMD and RMD and that both are equal, we require parse tree. So we are going to focus on parse tree in our next lecture.